So this is day 20, so video for day 20 on sorting algorithms. We're also going to talk about the portfolio for preparation. Okay. So we've already had heap sort. We've mentioned sorting before. So why are we going to spend an entire day on sorting? Well, because sorting, first off, is a very important thing that we do. There are so many things, so many algorithms you'll get in the algorithms class that are much faster if you have sorted data. So sorting's important. Okay. So also, it's just this is an advanced computer science course, advanced programming course. It's the most advanced programming course that everybody takes, all the majors take. So it's important that you understand the main ways we sort. Okay, so heap sort, merge sort, quick sort are the biggies. Okay, this section introduces one called counting sort, which is more specialized. And if you don't have much to sort, you can often do either a selection sort or an insertion sort. Okay. Again, if you go on to algorithms, you'll talk more about all of those things. Okay. So we'll start with merge sort. So merge sort is going to be a recursive algorithm. And again, I've asked Claude to create a demo for us that is mostly kind of okay. It's better than me scrolling on a iPad probably. Okay. So the idea behind merge sort, and we'll take a look at the example, then we'll look at the code, what it looks like, is that we have this array. Okay. We have 38, 27, 43, 3, 9, 82, and 10. Okay. And merge sort gets used almost exclusively to sort linked lists because they're easy to rearrange in this way. So the first thing we do is split. So we split this in half. Okay. So that's our first step. Okay. So we have the left half here and the right half here. Okay. We're then going to split it again. Okay. And then this split that left, it splits this into these two, the left left and the left right. Okay. And then finally, we're going to split that even further till there's just one. So we have the left left has these two elements and these two elements. Okay. Then we're going to start merging those back together. Okay. So we start with the 20, the 38 and the 27. We've got to put those back together. Okay. We put those back together, picking the smallest one first. So that's the 27 and the 38. Okay. We then look at the other one, the 3 and then the 43 are in the correct order. Okay. We're now going to further combine those together. Okay. So when we have this left and this right, the very smallest one is 3. It goes here. And we know that the smallest is always to the left of these because they came back up from being single one sorted. Okay. So we're comparing 3 and 27, 3 smallest. We remove that. We're going to compare 27 and 43. 27 is the smallest. Okay. We compare 38 and 43. 38 goes, and then the 43 goes. Okay. And then on the right side, we split that up into the right left and the right right. Okay. The right right gets split up again. We start merging it back. Okay. And then we get to the left looks like this, the right looks like this. These are both merged. So for the final answer, the first one, we were pointing at these two, and 3 is the smallest, it goes there. Then we look at the 9 versus the 27. 9 goes next. The 10 versus 27. The 10 goes next, and so forth until you get the sorted array. Okay, so that's what that looks like. Now let's take a look at the code for this. Okay. So the code for merge sort, again, it's best for linked list. It's going to, even though we're doing it with an array here, we're going to split it into two. Okay. So there's the merge sort part, and then there's the merge later. Okay. So this is going to go through. We've got the array, we're sending it, and we're going to call this recursively. So we have the low and the high, which is the current range of index values that we're dealing with. Okay. So that's what we're starting with. Okay. So if low is greater than or equal to high, then it's a base case with either zero or one element, and we're done. Okay. If not, we're going to create this mid, okay, by saying low plus high minus low divided by 2. We're then going to recursively call it on low to mid, okay, and then mid plus 1 to high, okay. And then finally, we're going to merge those two back together, okay. And this all creates, and this is all done recursively. So it's going to create all these different arrays and then put them back together. Okay. The merge part comes down here where we're going to combine the two together. Okay. So again, this takes a low, a mid, and a high. It creates a temp. Okay. Then it's going to go through and it's going to put whichever one's biggest or sorry, smallest next into the array. Okay. Then we're done. Okay. So that is merge sort. Merge sort is always going to be an n log n. Okay, big O of n log n. So big O, remember, is just given the n is the input size, how long does it take? Okay. Something else that you'll talk about in algorithms class is the fact that n log n is theoretically the fastest that a comparison-based sort can be. Okay, so we're at that. Okay. So quicksort takes a different approach. Quicksort is going to it's going to pick a pivot value. Okay. It either picks it at random, sometimes it picks the first, sometimes it'll do some calculations to determine what a middle range is. Okay. And then it partitions the array. A partition of an array is an ordering such that you have all the items less than the partition value, and then all the items greater. So it's a semi-sort. Okay. And by doing that repeatedly, we're going to be able to sort things out. Okay. So quicksort's used for things other than linked list. Okay. Um, the disadvantage to merge sort on an array is that it's just difficult to move all those things around and create all the subarrays, and it can be a little bit memory intensive. Okay. The quicksort doesn't have that problem, but the quicksort, the effectiveness of it depends on how well the pivot divides things up. So if the pivot doesn't divide very well, then it can go all the way to be a big O of n squared, which is not good. Okay. So here's our example. We have the same basic elements. Okay. As we go through, we're going to pick the last element to be our pivot. Okay. So we're going to pick a 10. So we're going to go through and say, well, 38 should be to the right. Okay. Of that. 27 should be to the right. 10 should be to the right. But 3 and 9 should be to the left. And 82 should be to the right. Okay. So it's going to go through. It keeps it there. Now it's going to move those around. See, it did a switch there to make that on the left. The 9, we're going to put it on the left. The 27, okay, it's going to stay to the right. And then we get back to the 10. And now it's going to put the 10 in the correct spot. Okay. So what we know when this is sorted, 10 is good. Okay. And then we're going to, that's after the first step that we have. Okay. And we're going to keep going until that gets sorted. Okay. Code of this one. Let me switch it so you can see, so I don't have to remake the video. I've done that already this semester. It's no fun. Okay. So here we have the quicksort. It does this, what's called a Lomuto partition, which basically is going to do this partitioning. Okay. So in this case, we're picking our pivot to be the biggest value. You can pick the smallest value. You can pick something in the middle. You can pick it at random. Doesn't matter. Okay. And then this I is going to track the last element that is less than or equal to the pivot. So that's the point that we're moving as we go through. Okay. And that's going to go do that. It's going to do the swaps when it moves the smaller elements to the left. And then the last thing it does is place the pivot in the final location. Okay. So that was the partition part. And then you have the Lomuto, which again, it's going to recursively call it. So once you've made the partition, you know that the pivot, so in our example we just did, 10's in the right place, but everything to the left now needs to be quick sorted. Everything to the right needs to be quick sorted. Okay. So that's kind of how that goes. Okay. And those are these two steps here. Um, so the last sort is it's kind of an odd one. It's more of a specialized one. And there are thousands of sorts in the world, just so you know. But this is the last one we're going to talk about in this chapter. Okay. And that's the counting sort. So what the counting sort does, the counting sort is only effective if you have a small range of numbers. Okay. So let's look at our counting sort here. So let's say we have these numbers that we want to sort. Okay. We're going to start by creating this count array. Okay. And we're going to assume that this array can only have values between 0 and 8. Okay. If this gets bigger, this becomes super not efficient. Okay. But if every value we know is going to be between 0 and 8, we're going to create a count array with the numbers 0 through 8. Okay. Um, we're then going to go through each time we see a 4. Okay. So we're going to put a 4 in the count array, put a 1 there. Okay. We see a 2 goes in the count array there. Another 2, we're going to increase that. An 8, there's one over there. There's 1 3, there's 2 3s, and there's 1 1. Okay. We're now going to go through and to sort this, there are no zeros. So the first element's not 0. Okay. There is a 1. The first element is a 1. Okay. There are two 2s, so there'll be a 2 and a 2. There's a 3 and a 3. There's a 4, and there's an 8. Okay. So there's the 1. There's the two 2s. There's the two 3s. There's the 4. Okay, no, nothing at 5, 6, or 7. There's the 8. Okay, now we have sorted that. Okay, so to take a look at what that code looks like. Okay, that's the counting sort here. Okay, it's again going to take an array and it's going to take how many elements we have, and it's going to take this max value. Okay, we're assuming 0 up to this max value. Okay, so then we're going to create this count. Okay, array that's initialized. Okay, we're creating this on the fly. Okay, we're then going to go through and in a for loop, we're going to fill that count array. Okay, and we're going to set the index equal to 0. Then we're going to go through again. We're going to do that actual counting. Okay, and then we're going to delete the count that we've created once we're done. Okay, so those are the different sorts that we're talking about. Okay, so um, all those have different times, different things that we do with them. Okay. So the last thing I wanted to talk about today is Lab 20. And we'll also just kind of look at what we've covered so far. We're most of the way through the course now. Okay. So Lab 20 is going to be a benchmark lab. We're going to implement the merge sort and the quick sort with both the plain. You can also do a random pivot and also the counting sort. Okay. We're then going to run all 5 of those sorts, so the 2 versions of the quick sort plus the heap sort makes 5, okay, across 4 different input types, either random, sorted, reverse sorted, and all equal. And then you're going to create a benchmark write-up markup file, so a benchmark underscore write-up.md that will put the results of that, okay? Um, and this 4 weeks of the course that we've covered. Okay, we've done a lot. We've done a lot of stuff. It's happened quick. So we've built from scratch a stack, a queue, a deck, a linked list with an iterator, a binary search tree, a heap, and a hash table. Okay, that's 7 distinct data structures and 5 sorting algorithms. Okay, we've also measured the performance both empirically by running tests and reasoned about it theoretically. Okay, which is all good stuff. Okay. So go ahead and get started this weekend on Portfolio 4. Okay. So that's going to be something you definitely want to finish up. Okay. Um, and next week we're going to talk about graphs, the mathematical graph. We're going to talk about breadth first and depth first searches, or going through the algorithm or the structure in that way. And we'll talk about Dijkstra's algorithm, which will appear again in the algorithms class. It will also appear in a networking class, most likely. Okay. And then we'll talk about the final portfolio. Okay. So the heap that we built this week will reappear in the Dijkstra's priority queue. Okay. So that's it for now. So if you have questions, as always, go ahead and let me know. Again, all the material should be available always. So if you find yourself with a little extra time, it's a good idea to go ahead and work ahead whenever you can. Okay.